All right. Today we would like to talk about the most fundamental circuit, current sources. Yeah. Anyway, we talk about the most fundamental devices, just like diode, MOSFET, and then what we can do with all such kind of devices. The simplest one actually is the so-called current sources, and then in next week, you just go to the computer lab. Don't come here. That is the very good timing for you to have the first homework. Anyway, why we need to focus on current source? Simply because in analog IC design, actually we focus very much on bias voltage. We focus very much on bias current instead of bias voltage. Yeah, but anyway, not only for bias, but also for such kind of active load. What does it mean? For load, usually in the past, we have resistor. But on chip, resistor usually takes a lot of chip area. It is expensive and also noisy because the free electrons conducting in such kind of resistor should always need to collide with the crystal. Yeah, so it generates a lot of thermal noise, EMI interference, blah blah blah. So hopefully we can replace such kind of passive resistor with active load. What does it mean? Current source. Yeah, because what is the property for current source? We hope, in idea, the output resistance can be infinite. Okay, so according to resistance, wow, if your resistance is infinite or it is very large, what does it mean? With the same resistance, it only takes us very little, very small area. That is what we need. Okay, so anyway, that is the most important 2 points for current sources. One for bias, the other one for active load. And this is our outline for today's class. From the very beginning, even BJT is seldom used, but according to technology evolution, circuit evolution, humankind tens of years ago focused on this, then migrated to next. So we would like to still complete the process, because if you look back to the past, you can learn something, just like humankind's history. Don't kill each other, blah blah blah. Hopefully we can learn something from our history. The same for BJT. Yeah, that is the first humankind's focus. So a lot of technology is actually were created in that era, then migrated to the next, right? So we can learn something from the past, then open to our new future. Yeah. Anyway, what is the ideal current source? It should look like this. Okay. What does it mean? For a current source just like this, what's your expectation from circuit theory? That means what? Never mind what kind of terminal voltage you apply to such kind of current source, the current cannot be changed. That is the most fundamental requirement, right? So this is what I have for you. Not only this, but also expand to the negative part. Anyway, anyhow, that is the fundamental requirement for current source. But if you look back to, if you look at the negative part, what does it mean? For negative voltage, it can still provide positive current. Yeah, that is the, how can I say, functionality of battery. Okay, because you can see what I'm talking about is battery. If you look at the direction of the current, It is reversed. It is reversed to the voltage, right? So according to P equals IV or VI, that is positive, that is negative. Well, you have negative power consumption. Oh, what does it mean? Power consumption is usually positive, right? I mean for resistor, positive here, negative there, so the current flows in this way. So both are positive. So you consume positive power. It makes sense. But what does it mean? You consume negative power. Oh, it means what? You generate power. You generate power for the others. So you become a battery. Here, it will be a battery. So in idea, you need to cover both sides. But in practice, for the negative side, it will become a battery. It's usually non-necessary. Okay? So we are more than happy to focus this. We don't focus on battery, usually. Yeah. Our power actually is supplied by the others. So we are happy, more than happy, to focus on this. Anyway, anyhow, you had better to see two very important properties we expect. First of all, I told you already, the slope needs to be 0 because never mind how large variation you put on voltage, the current cannot be changed. Okay? And the second, yeah, I highlight here, no headroom. What does it mean? Why no headroom? It means what? Since V positive larger than 0 or even equal to 0, you need to provide such kind of constant current. Okay. On the contrary, this is in practice, in theory. And what is in practice? Later, I will show you. So, before we leave this slide, I would like to point out that this is the role. This is the key role for our bias current. Yeah. For the circuit, then if you would like them to operate, you need to supply proper bias, right? Here, bias current here. If you would like to apply bias voltage, later I will show you. All right, it is not so good on chip. Yeah. Then we go for such kind of the simplest idea, simplest structure about current mirror. Yeah, we call it basic or fundamental current mirror. 2T means what? Only 2 transistors. That is the definition. If you look at something, you have 3T SRAM. Oh, it means only 3 transistors can compose your static memory. Yeah, that is really hard, but it exists on Earth. Okay, that is the most fundamental current mirror. What is the definition for mirror? If you look into the mirror, you will see yourself exactly the same. So that is from the very beginning, current mirror means the output current should be exactly the same as the input. Okay, just like you look into the mirror, you see yourself exactly the same. If not the same, then you see some ghost. Yeah, hopefully not. So this is we have Q1 and Q2. If they are exactly the same, then hopefully the output current will be exactly the same as the input I reference. Yeah, anyway, piece of cake. Just derive it by yourself. That's too easy, okay? But anyway, I would like to tell you that for such kind of BJT, yeah, to make both Q1 and Q2 functional, you need to provide proper bias current to their base, right? Wow. So what does it mean? For IREF, actually, it provides not only what? IC1, but also 2 IBs. And how about our output current? Output current only equals IC2. So if nothing wrong, if Q1 and Q2 are exactly the same, to the most, you can expect IC1 equals to IC2, right? But IO only equals IC2, so forget about it. It doesn't be the same as IREF, right? According to IB1 and IB2. But how much is IB1 and IB2 according to forward current amplification factor? 顺向电流争议。Anyway, you can see 1 here, beta there, and beta plus 1 to the emitter, blah, blah, blah. Okay, so if this is 1, then this is only 1 over beta. But 2 of them to cause the error, I mean the mismatch between output and input. So this is what I explained for you. Yeah, according to IC2, according to I out, compared to IREF, you have almost 2 over beta % in difference. That is inaccuracy. That is the so-called error. Okay. Not only that, but also in BJT we have such kind of early effect. Oh, what does it mean for early effect? This is the so-called early effect. And you learn already from your microelectronics. Yeah, so you can see the slope is not 0. So if you extend it to the negative portion, you will get this. VA means the early voltage. Yeah, anyway, we still hope in this region, in BJT we call it linear region, okay? But in MOSFET, we call it saturation. I have no idea why. They talk about the same thing, but with 2 different definitions. Yeah, anyway, just think about this. For MOSFET, it is called saturation. What does it mean? The output current is saturated. Hopefully, it doesn't increase even you increase the voltage, right? That is what we expect. But nothing is perfect. This is not 0 for slope. So, yeah, we hope the larger VA, the better. But why we focus on this? Simply because if you look at the structure, this is the input, that is the output, right? So if the voltage here and there are not equal, usually not, sorry for that, okay? If they are not equal, even though Q1 and Q2 are exactly the same, all right, they are the same. They have the same curve. They have the same characteristic curves, even though. But if VC1 and VC2 are not the same, so your current here, that is for IREF. Even for IC1, I mean even for IC1, okay? And that is for the next. The first one, the next one, sorry for that, their current won't be equivalent, okay? That is a very sad idea. So, even for such kind of very simple, the simplest current source in BJT domain, yeah, we have 2 errors, 2 kind of errors. First of all, it is caused by beta. If beta is infinite, oh, congratulations, this will be 0. But it never be infinite. Okay, that is the ideal case, but in practice, no. And how about the early effect? The same. Sorry for that. Only if VC1 and VC2 are exactly the same, you can neglect early effect. Otherwise, you need to consider it. 2 major errors caused by such kind of very simple structure. That is what you need to know as an analog IC designer. You need to know its merits and demerits. Okay? For merits, you say, oh, in the future, I need to apply this for what? Because it has some kind of advantages. Okay? But why you still need to know about the advantages? I mean, the demerits, disadvantages. Simply because you need to cancel it if you have the power, but usually not. Okay, you can reduce it. Okay, you try your very best to reduce the disadvantages and to enhance the advantages. That is what you need to do, yeah, to be a very good analog IC designer. Okay, that's it. And then, never mind for beta or early effect. I always assume what Q1 and Q2 are exactly the same. Okay, because I'm really cautious. Under such kind of ideal condition, you still have two major inaccuracies, major errors. Okay, if the assumption is not correct, I mean Q1 and Q2 are not exactly the same. Wow, it will be even worse, right? Even bad, even worse. Okay, so what is the definition? If they are the same, that is the perfect, that is the ideal condition. But in practice, Q1 and Q2 never be identical. Okay, why? Okay, allow me to show you the most important equation for BJT transistor. Look like this. Yeah, your output current equals to IS means scale current or saturation current. Yeah, I explained already in chapter 2, chapter 3, from diode all the way to BJT, right? Or MOSFET. Anyway, exponential, blah, blah, blah. So the most issue is that the scale current won't be exactly the same after fabrication. Yeah, because the scale current depends on the base doping, base width, emitter area. After fabrication, I promise you, nothing will be the same. No, forget about it. Okay, that is really upset, but that is also our real life. Nothing is perfect. You need to face such kind of non-ideality and try to deal with them, try to reduce the impact. That is what you need to do. All right? So, if they are not exactly the same, we always say they don't match each other, or they are not fully matched. And it means we have some kind of mismatch. Okay? Miss means not. Okay, that's it. Mismatch. They cannot be fully matched. And how to reduce such kind of mismatch? You can see Q1 and Q2 had better, very close on layout. They need to be very large. What does that mean? Yeah. For random, there are two kinds of mismatches, as I mentioned in last class. In previous semester, the standard deviation. Yeah, of any kind of mismatch. Yeah, it should be reversely proportional to the square root of the device area. So it means the more area, the less deviation, right? That's it. Yeah. So hopefully, for critical devices, if you think the mismatch for your current source, current mirror is really important, then hopefully you can have such kind of large device. Okay. And then you need to have such kind of cross-couple connection. What does it mean? The simplest is 1, 2, and 2, 1. That is simplest. And it means the transistor Q1 and Q2, right, needs to be split into halves, 50%, I mean, right? And then 50% here, 50% there, similar for 2. Oh, congratulations. In this way, you can reduce. Again, you can only reduce instead of cancel the mismatch. Okay? As a humankind, you need to accept such kind of condition. We are humankind, we are not gods. So nothing is perfect, nothing is ideal. You need to accept such kind of yeah, non-perfect conditions. So to the most, you can only reduce mismatch instead of cancel it. Cancel it means what? Reduce it all the way to 0. Okay, yeah. That is the definition. Forget about it. So even for such kind of very simple circuit, the simplest circuit for analog IC design, it still has a lot of non-ideal properties. What we can do? Okay, we had to better improve it. Yeah, we are humankind. We are talented, right? If you face such kind of difficulty, don't be upset. Oh, they are not the same. Or a lot of problem according to VA and also beta. What is life? This, forget about it. Yeah, go for AI. And if you go for AI, a lot of problem there. So forget about it. No, that is a really bad attitude. Just face it and think. Usually, if you face any kind of difficulty, not only you, but also all of the others. So how can you make yourself outstanding? I mean, different from the others. Face it with positive attitude, and then try to think how to solve it. That is the best idea you can do. Okay? Anyway, how to improve the accuracy of such kind of current source? I mean, how to reduce the errors. All right, allow me to show you. Here, you can see Q1 and Q2 composed of the fundamental current mirror, the simplest current mirror, right? But Q3 will help you to reduce the accuracy according to beta. That's it. Yeah. To my memory, this is a pattern from Philips, if I am right. Okay, years ago, yeah, I Googled, like, wow, I suddenly found that for such kind of very simple idea, Philips paid a lot of money to apply patents, yeah, around the globe. Okay, but luckily enough, that is long time ago. So right now, you can be more than happy to apply it. Yeah, Philips wouldn't like to sue you because it is already out of date. For patent, usually it takes 17 years instead of 70. 17 good enough. But that is for such kind of patents. Such kind of patents. For video, audio, under the huge, how can I say, stress, yeah, from America. I guess much longer than this. Just like the songs from Disney for the kids, right? Forget about 17. I guess maybe 70 years. Because America is very strong for such kind of culture exportation. But for all the other goods, usually they import, right? They only output their culture, their logic thinking. Okay, so what is the function of Q3? I told you already. From the very beginning, BJT is used to amplify IB to IC or to IE. Because one here, beta there, and beta plus 1 at E terminal. Right? So if you look at from base to collector or base to emitter, it looks like an amplifier. Right? But here is not directly related to amplification. No. On the contrary, we would like to use in a reversed way. 反过来用. Okay. So what do I mean? On the contrary, right now, I wouldn't like to look from base to emitter or to collector. No. Reversely, I would like to look back from emitter to base. If you look at here, it is amplified by 1 plus beta or beta plus 1. So reversely, if you look from emitter to phase, congratulations, you get the so-called attenuation, because 1 here become 1 over beta plus 1. Bingo, that is the key idea. But why? Very simple. You have 2 IBs here to cause inaccuracy. So with the help of Q3, because in the past, if you look at the original structure, it's really upset because all those 2 IBs are connected directly to I reference. It causes such kind of huge error. How to reduce it? If there is an attenuator, 衰减器, from here to there, I can reduce the order by how much? By the attenuation factor. That's it. Okay, so this is a very simple idea you can learn from such kind of very old circuit. Even humankind created this circuit tens of years ago, but you can still learn something. Even though it is out of date already, even though that is only for BJT, but you still can learn something. Okay, so the same IBs, but with the help of Q3, as I mentioned, from here to there, right? The magnitude will be reduced by how much? 1 over beta plus 1. Here. Congratulations. With the help of Q3, the error will be further reduced by this factor. Okay, so from the beginning it is beta 2, and right now, congratulations. So how much is beta? Usually for BJT, 100, around, but with a lot of variation mismatch. Okay, later I will explain a little bit about such kind of mismatch. Yeah. Anyway, so in the past, you can guess the magnitude for mismatch is around 2%. But with the help of the other term, for attenuation, right now, yeah, it becomes almost 0.2%. Bingo. From 2% to 0.02%. Very good. Very, very good. Okay. So what is the price you pay for Q3? 1 extra transistor. But 1 extra transistor means because in the past Q1 and Q2 from 2 to 3, right? Almost only 50% increase in your chip area, but it can help you to improve the property to reduce the mismatch by 100 times instead of 100%. So it is a good bargain, right? 50% more, but 100 times better in performance. Bingo. That is what we want. And this is the reason why Philips applied this pattern to kill all the others. Yeah, don't use such kind of pattern. Otherwise, if you violate, I will sue you to get a lot of money. Okay? And this is what I can tell you. In the past, yeah, that is the beta, right? But how about beta? Beta has a lot of variation. Why? It is related to its fundamental structure. Yeah, if you have any idea, you will know that is the fundamental BJT structure in the past. Yeah, it has 3 terminals. A discrete component, a discrete BJT look like this. If I have the cross-sectional view for you, I slice it to show you, okay, the semi-circle. Yeah, you will see emitter here, base and then collector. That is a very fundamental structure. Again, I think you learned already from your microelectronics, but yeah, allow me to refresh your mind. Especially, I would like to point out something maybe you never learned from your microelectronics. Yeah, for NPN, for NPN or PNP, I don't care. Emitter needs to emit majority carriers, so it is highly doped. Okay, and collector is used to collect all the carriers emitted from emitter. So it doesn't need to be highly doped. Usually it is very lightly doped. And then base behave as a controller to just like the tape, right? To turn on the water, to turn off the water, and how much the water you would like to turn on. So base is a controller to control how much carriers emitted from E will be collected by C. That's it. As a controller, just like the tape, you hope that is the controller. The water here, right? 水龙头. So according to such kind of switch, to turn it on, to turn it off, what would you expect to have? This is the emitter to eject, to emit a lot of carriers, then collector here to collect them, right? And a base here to control. Sure, you expect all the water will flow from E to C instead of from B. Otherwise, you have some kind of water leakage here. It doesn't make any sense, right? So to reduce the leakage at the base, the base needs to be very, very small. I mean in thickness. Okay? And again, the overall area for base, because it's really thin, really, really thin. It means what? Again, the standard deviation. So that is what you need to face. Okay? Wow, it's too messy. Clean it for you. Anyway, the base needs to be really, really thin to reduce the current leakage. All right. So very small current will flow through B. That is what we need, because IC or IE should be much, much larger than IB. It means what? Beta can be as high as you expect. So that is by nature. According to humankind's expectation, we hope beta can be as large as possible. So it means the base region to be as small as possible. But according to, again, the random mismatch look like this, the standard deviation of anything, okay, including beta. And who controls beta? The area for B, okay. The smaller, the larger, the smaller B, the larger beta. Congratulations, but according to such kind of idea, the standard deviation of beta will be reversely proportional to the base area, right? The base area is really small, so you need to face such kind of consequence. Very huge deviation in beta. That is what you need to face for such kind of discrete BJT. Discrete BJT can provide you very good beta, but with a lot of variation, huge standard deviation. On the contrary, especially for our CMOS, we have parasitic BJT. Okay, according to its structure, if you look at this is the emitter, highly doped, then beta, and then base, and then the huge area for collector. Yeah, that is layout. That is the layout for parasitic BJT on CMOS chip. You can see you have huge area of beta. What does it mean? A lot of current leakage, or leakage current as you like. Okay? So beta is reduced substantially from 100 to almost only 10 or even less than 10. That is the bad. That is the demerit, but it's also the good. Why? Since they are twins, the good and the bad, 好事坏事，他们是孪生兄弟。Okay, why? Because for such kind of parasitic BJT, I told you already. Why? The beta is really bad. Simply because the base area is too huge. A lot of current will be leaked from your base region. And this is the reason why beta is reduced substantially. But according to standard deviation, right, the beta area is increased very much from the discrete component. So the standard deviation is reduced very much. Bingo, that's it. So for such kind of CMOS parasitic BJT, usually the engineers complain a lot about the beta. Oh, the beta is so small. What is the function? What is the useness, the usefulness of such kind of very low beta BJT? Oh, the beta is really stable with much smaller deviation, yeah, from its discrete component. Yeah. So please keep this in mind. If your circuit depends on beta, then maybe you had better don't use such kind of parasitic BJT. However, if your circuit doesn't depend on beta, yeah, it depends very much on the stability of beta, then use it. Parasitic BJT is much better than discrete BJT for stability. Okay, yeah. And then look at this. Because beta varies a lot of mismatch, right? So a lot of variation on beta, so you cause also a lot of variation on such kind of I/O mismatch. Okay, but that is only for single beta. If you apply Q3, you can reduce the mismatch by 1 over beta plus 1. Then you will see the output current will not only very close to input, but also stabilized very much. Okay? Very good. But you improve only the accuracy. I mean, you try your very much to match I/O to I reference. However, you still only have Q2 for output. What does it mean? From the output, if you look back, you get only RO, output resistance of Q2. Yeah, according to early voltage. And how much is this? Around 100 kilo ohms. Sometimes it's not good enough. It's not good enough. Okay. Again, yeah, it is related to the slope. The larger resistance, output resistance, yeah, the smaller output slope, right? So it means never mind how much voltage in variation, you cause very small difference for your output current. That is what we want. The larger, the better. Okay? But right now, Q3 only help you to attenuate to IBs, but it doesn't contribute anything to your output transistor because it looks the same. If you look back, it's still RO2 for your output resistance. Nothing is changed through Q3. Okay, so yeah, you get very good improvement in the I/O accuracy. But for output resistance, nothing happens. Okay, let's go further. How to enhance the output resistance by cascading? Okay, very, very important idea. Humankind created maybe more than 100 years ago, more than. That is what I guess, at least tens of years ago. But till now, we still apply it almost every day for analog IC design. Okay, unless the voltage become too small, otherwise we still apply it. The so-called cascoding. Very important idea. Okay, so what is the function for Q4? Cascoding. The most important issue is, again, where is your current mirror here? Don't get any kind of misunderstanding. Who controls your current? This. Okay? I will say, hey, so what is the function of Q3 and Q4? Especially for Q4. It is a current buffer. That is the original idea for cascoding. A current buffer. What is the definition for current buffer? Okay, I think you guys are much familiar with voltage domain. So allow me to ask you, or allow you to ask yourself, what is the function for voltage buffer? For voltage buffer, it means what? No voltage gain. No voltage gain. In voltage domain, what do you want from such kind of no gain buffer? You need to have very high input impedance, very low output resistance, right? And why? Don't ask me, okay? That is the very fundamental idea. Yeah, that is too low for me. I'm your analog IC teacher, okay? Not fundamental microelectronics teacher or fundamental circuit teacher. Okay, anyway, that is for current voltage buffer. On the contrary, if you look at the current buffer, the properties need to be totally changed. Again, no current gain, right? The input current in idea should be exactly the same as your output. Bingo, that is the key idea. And then the input resistance should be 0, as close to 0 as possible. Why? Because I would like to sink all the current from the input. 100% of the current will flow through myself. And then 100% will be output to the other side. Okay? But how can you promise this according to Norton's equivalent circuit? Okay? For I, right? How can you promise 100% from the input to the output? According to Norton model, from the input, you have input current, you have input resistance. How can you promise me 100% of the current will flow into the buffer instead of here? I have 0 resistance. I absorb 100% of the current to my side. According to you have resistance, I have resistance. The smaller, the more you can get. Right? I mean for the current. So the best idea is to get 0. That's it. Very, very low resistance. I can absorb almost 100% of the input current. And then how can you promise me to output 100% of the current to the load? Yeah, that is yourself again. Your input have such kind of model. Yourself still have such kind of model. Because we are talking about current instead of voltage. We need to apply Norton equivalent circuit, Norton model, circuit model. Okay? So how can I promise the current I absorb from the input? How can I promise you I will push 100% to you? Bingo. If my output resistance is infinite, I will push all the current to you. Okay? Very simple idea. Okay, so what is the property for current buffer? Again, AI should be 1. Okay, 100% of the input current should be passed to output But how can you make it? Very low input resistance, very high output resistance. Bingo. So if you have such kind of current buffer here, I need to congratulate you. Yeah, because to the output, and look at the output resistance of such kind of current mirror. It is infinite. In idea, bingo, bingo. Infinite means what? Finally, we make it. It is flat. The output I to V, right? The output current will be flat. Never mind how much voltage you apply to it. Congratulations. But that is only in idea. Okay? In practice, it cannot be infinite, but it can be much, much larger than before. I mean, through the help of the current buffer. Okay? So, Q4. Please keep this in mind. Q4 for cascading, actually, it behaves like a current buffer. And this is why I'm different from the other professors. Okay, I explain everything to you, but I don't derive anything for you. That is your own responsibility. I think on earth, very few professors will teach you in such kind of detail. I mean, for concept. Okay, this is a buffer, a current buffer. Okay. Again, if you look into Q4, the resistance is really small. If you look at the output, according to cascading, that is the result. Derive it by yourself. Fine. If you are curious, please go back to your microelectronics. Okay? But it's really simple. You just apply the small signal equivalent model, blah, blah, blah. You can derive it by yourself. Don't waste your time or my time. Okay? Especially, you get such kind of equation from your microelectronics again already. All right? Okay, but I would still like to help you a little bit more. If these are really large, usually that is the case, much larger than 1. Since it is so large, much larger than 1, so you can neglect 1, right? Okay, so what I can help is the output resistance becomes what? Becomes what? Okay. I cannot say the emitter resistance. No. I prime. I prime means what? The resistance look at terminal E. Okay? Then all the equivalent resistance at E terminal will be amplified by your what? GM and RO. Okay, that is really important. Your own GM. So if I would like to write in more detail, see, 4. Okay, as a current buffer, what is my major function? I will enlarge the overall output resistance. Yeah. From the beginning, you have RE prime. Okay, I mean, without Q4, you have RE, right? With Q4, you have RE prime. Hey, why? A little bit in difference later, I will explain. But anyway, anyhow, the RE prime will be enlarged by myself, GM and RO. Myself, not the others, okay? Don't make any misunderstanding. That's it. How about GM, RO? What's the order? Usually 100. So what does it mean? Bingo. Wow. With the help of current buffer, I mean with the help of cascading, the output resistance will again be increased by 100%. Okay? Wow. 100 times, sorry, 100 times. Wow. Again, it's a really good bargain. You only pay extra money for Q3 and Q4. And what is the function for Q3? It needs to bias your Q4. Okay, that's it. For your Q4, to make it active, to make it functional, it needs to get proper bias. So Q3, the major function for Q3 is to provide proper bias to Q4. That's it. Okay, Q3 is not a cascading transistor. No. Why? Because its collector is collect to base. So the overall resistance is really small. So this is not for cascading, only Q4. Good. Okay, for cascading. Okay, before leaving this page, I need to highlight RE prime is not RE. Okay, you need to be very careful. Why? Because for the equivalent small signal model from base to emitter, right? This is RO, and this is input resistance HIE. So at terminal E, you have RE, right, to the ground. And also, because this is the stable bias voltage, it can be viewed very close to AC grounded. Small signal is for AC instead of DC, all right? All right, so what I'm talking about is AC grounded instead of DC grounded. What is the difference? If the voltage, if the DC voltage is fixed, 1 volt, 2 volt, any kind of volt, then for AC it is grounded. Because delta V is 0. That's the definition. Yeah, delta. Yeah, for your AC. Okay. Anyway, so what is the RE prime? It is RE in parallel with HIE. That's it. Bingo. That's it. All right. So before our break, yeah, again I need to get my coffee. But anyway, what is the function of Q4? Anybody? Current buffer. Okay. What is the merit? What is the advantage you can get? 100 times increase in output resistance. Right? But I am only talking about the merit, the advantages. How about the disadvantages? You can see the headroom becomes much larger, almost twice, almost doubled than before. Okay, that's it. Yeah, you can see the real, okay, I forgot to show you. Right? That is the real property for current source or current mirror. This is so-called headroom. It means what? Before some point, it is in such kind of very bad region. In most of it, we call it triode. Okay? And in BJT, I forgot. BJT called this linear. Maybe this is the so-called saturation region for BJT. The definition is totally reversed. Okay, but anyway, yeah, this region no good because we hope. Why? It is no good because a small change in V will cause a lot of change in output current. Oh, it doesn't make any sense. I'm a current source, right? My current had better not be changed anymore. All right. So we would like to work here instead of there. So we call it a headroom. Within headroom, the current mirror, the current source is broken because the property is really bad. Okay? It never be any kind of current source here. It is malfunctional. It is not functional. 它是错误动作了，在这边是不能工作的。Okay, that is definition for headroom. So what is the price you need to pay? Not only Q3 and Q4, but also headroom will be almost doubled. It means originally it looked like this, and right now it is doubled to there, right? But what is the gain? The slope is almost 0 because the slope is reduced by 100 times. Okay? Yeah. And this is also another ugly truth you need to accept. You see, I help you to reduce the slope by 100 times to make it very flat. Right? This is the good for you. But nothing is perfect. You need to pay for, usually you need to pay for this. Okay. Headroom becomes larger. Yeah, that is the ugly truth. And for the circuit later, I will explain. Yeah, we have some We have some technology, some structures to help you reduce the headroom. Oh, very good, very good. Then I promise you, usually you need to pay for output resistance. The output resistance will reduce substantially. Okay? Is there any circuit that can help you reduce headroom and also enhance your output resistance? I cannot say it is something of mission impossible, but I need to warn you, it's really, really, really difficult. Okay? As a normal humankind, you need to accept, I enhance this, but on the sacrifice, with the sacrifice of the others. 你要获得这个，你就牺牲别的。Okay? Yeah. So you need to do some kind of trade-off. That is a very good and important altitude for analog IC designer. Don't try to make everything good. Don't try to enhance, to improve everything. If you have such kind of attitude, I promise you, you will make nothing. Okay? Because it is really, really, really hard. Yeah. Or sometimes you make it, but the price is sky high. Yeah, you will be fired by your bosses. You spend too much effort, too much money on such kind of enhancing almost everything. You will lose your job. Okay, very simple. So don't try to make such kind of silly idea. No. Try to do such kind of trade-off. It means, for example, what is important for you, for your application? Higher resistance, output resistance, or smaller headroom? It depends on, it's up to your application. Okay? Usually, we don't require both. For example, if you will go to very low voltage, then smaller headroom is much more important than output resistance. Okay? On the contrary, if your supply voltage is high enough, then you can sacrifice, you can trade your headroom with what? Larger output resistance. Be smart. Okay? Don't be some kind of ideologist. Yeah, just like ISIS. Yeah, they are IDE. They have a very good idea, but it is not good in practice. Anyway, trade-off. That is a very good altitude for analog IC designers to have. Don't expect you can make everything. If you have such kind of attitude, again, I warn you, usually you make nothing. Okay? You can only make something instead of everything. All right? So we can have a break right now.